So we talked about the problems of estimating the theoretical limits of mechanical strength last time. And it's 17. That 17 is an overestimate because not all the bonds share the load, let alone not all the bonds break. And this leads to lots of confusion that I have reviewed already based on this wrong estimate of the theoretical strength. So the question, of course, is why do you have a difference, which is already wrong? We know it's wrong. We know we observe something like 150. Well, you see, the problem is if this is wrong, then we don't have the job of reconcile why they are different by 2 order magnitude. But one way of proceeding, at least I hear such rumors, or one approach of thinking about this is to say, oh, you observe a much lower stress because you have flaws. Or in other words, let me raise the question. So how do we know the limiting strength you observed is not a result of flaws? And so that's the question. So the way to think about this is indeed the subject of thinking about fracture mechanical aspect of glassy polymers. So let me just mention some efforts in that, in the sense if you have a cut, then indeed people have learned from Griffith's criteria and start to look at what critical stress the cut will go through, will become a brittle or failure. So they have observed that for polystyrene, there will be a critical stress depending on the cut length where the failure occurs. So they find out that if you introduce energy release rate, and they find a critical value at which polystyrene would fail. And they found that this value is about 1,000 joules per meter squared. Okay, so one could try to estimate what is the surface fracture energy. And you find that if you really think all the bonds are breaking, you can estimate and find that this energy is on the order of 1 joules per meter squared. And of course, this formula is based on assuming that, let me just flip the page. It's based on assuming that all the bonds are broken, consuming an energy level of all the bonds are broken. That's the density of the bonds, number of bonds per unit area, and all the bonds are undergoing scission on the order of 200 kilojoules per mole. So you end up having a value that's about 1 joules per meter squared. And that's an overestimate because not all the bonds, as we indicated before, not all the bonds, just like the way we estimated the strength, same way we estimate gamma, there is this overestimate because not all the bonds are presumably bearing load and undergoing scission. Therefore, this gamma presumably should be the low-bearing strand density times whatever energy consumed, whatever density that was involved, whatever energy that's involved in failure of that surface. So conceivably, this is if I allow myself to call this gamma 0, then I can say that the real gamma is probably smaller than the gamma we just indicated here by another factor of, let's say, 10 or so. So this could be as small as 0.1 joule per meter squared. And compare that with GC of 1,000, they are 4 order magnitude apart. So clearly, there are issues with understanding why you have such low strength. There are issues if you just use fractal mechanical approach to explain it, is what I'm trying to say. Because of this 4 order magnitude difference. So, so this is a fractal mechanics that I'm not going to go into any detail here. I'm merely raising the question of why we have such low mechanical strength. Well, when I say that, I already misspoke. If you say your mechanical strength for polystyrene, okay, is only, let's say, 30 megapascals, the total strength. I mean, I lose a good word, so let's call it the brittle strength. We have no idea whether how to think about this level of stress unless you know the theoretical limit of your strength. And we went through the class and suggested the way to think about that strength should be low-bearing strength, and however amount of force required for the network to fall apart. And we have no reliable estimate of this, nor do I have reliable estimate of that. Except we know that they are not the density of phi and breaking force of the chain, which would give you 17 or 15 gigapascals for polyethylene, for example. So for polystyrene, it would be a factor of, let's say, it will reach, for styrene, it will probably something like 5 gigapascals. So of course, we have, again, a factor of 100 difference, but we are misled by thinking there is such a difference because this is untrue. And the true value of this is unknown currently. That's the reality. So in short, if you recall fractal mechanics, it was initially motivated to exactly explain why the observed strength is so much lower. That's what Griffiths did. So much lower than what? So much lower than the theoretical estimated strength. So if you're unable to estimate the theoretical strength, then it's not clear you should call for fractal mechanics to come in. That's the logic. Or I flip that question around. When you have material that has reached a certain limiting strength and it's brittle, let's say, there is no reason to say per se that to understand the brittle failure of that material, you necessarily have to blame that there are flaws in that material. So I think we are basically in this dilemma. Exactly this dilemma. Therefore, I just want to clarify that all the discussion we have had in this class, polymer physics, we have not taken into account of any impurities, maybe one way to say it, bubbles, voids, parts, visible or not in our material. We have discussed an idealized case where in absence of any flaws and defects, we can still entertain the question of what would be the strength or what need to exceed for you to break your material. And in particular, in the case of glassy polymers, we recognize the phenomenology that above certain temperature is ductile, below certain temperature is brittle. And we speculated that this brittle failure has to do with the network falling apart without being able to say anything quantitative, actually. So this is the difficulty of not knowing that this is really very close to theoretical strength or not. So I think it's widely open how to proceed from this point. So here I did use the opportunity to indicate that when you, I think this is clearly in the spirit of blaming that my brittle polystyrene fail at 30 megapascals is a result of flaws. Otherwise, you wouldn't apply fracture mechanics. And people did. They applied fracture mechanics. To our disappointment, we find the critical energy release rate is 4 order magnitude smaller than the surface fracture energy. In fact, if you really think that this gamma or this gamma 0 is so-called surface tension, then you know our organic polymers, the surface tension is typically even another order magnitude smaller. This you should all know. Water is of that magnitude. Any organic material, it would tend to be of that magnitude. So that will give you about 5 order magnitude of difference. And the question is this: when you have 4 order magnitude difference between GC and gamma, is it good enough for you to blame that this is just because we have not included processes such as plasticity and plastic deformation? Where for polystyrene, well below brittle ductile transition, it appears, at least in our theoretical analysis, they are really not capable of undergoing any plastic deformation. Therefore, there's some logical problems by blaming that this 4 order magnitude difference for something such as a plastic deformation. There could be other things that you wish to dream about, but I will not go further along this line, but just raise the question of how useful fracture mechanics is here to help us understand the fracture behavior of rather brittle polymers, where supposedly fracture mechanics should work very well. Okay, so I will just stop here.